All right, so picking up kind of like in the middle of the problem, not ideal, but I think y'all can handle it. Just to review, we were given an equation. It was a quadratic, and it described the position, the location of the particle on the horizontal number line, which we could say is the x-axis at any given time t. Distance is measured in feet, time is in seconds. So we had just busted out the calculus on part C. When we were finding its instantaneous rate of change of position, also known as velocity, right? At 0 and 3. So I think we finished both of those, right? Yeah. All right, so that brings us to part D. Find the acceleration of the particle when t is 3. Find the acceleration of the particle when t is 3. Is that instantaneous or average? How do we know it's instantaneous if it doesn't say instantaneous acceleration? When or at that moment in time, right? Explain its meaning in terms of the particle's velocity. Okay, so to find the instantaneous acceleration, all we got to do is plug 3 into the acceleration equation. Do we have the acceleration equation? No, we don't, but we can get it very quickly by using calculus when we take the derivative of our velocity equation. So if you hadn't called x prime v, you would now need to take its derivative and call it x double prime. But if you called it v, like I recommended, then you could just say v prime of t, and then I would give that a name as well, a of t for acceleration. So that's important because that defines a new function. And now using the power rule, derivative 2t minus 4 is just 2. So we have a constant acceleration for any given value of time t. But that doesn't quite answer the question, right? Now it says to find it at 3. So notationally, we do need to make the distinction. So now we'll say a of 3 equals 2. And now it's my final answer. So we need to put units on there. And what would the units be? Acceleration. We're talking about feet and seconds. So feet per second squared. Yeah. Okay. So there's your numeric answer. Now, acceleration is a vector. Okay. Believe it or not. So when you have a positive acceleration, that means the velocity is increasing. When you have a negative acceleration, that means the velocity is decreasing. All right. So this is a positive number. Now it says to explain it, that means write a sentence in terms of the velocity. So we're not just going to write a sentence and say at t equals 3 seconds, the particle's acceleration is 2 feet per second squared. We got to get the word velocity in there. So acceleration being the rate of change of velocity, and acceleration here being a positive, we need to say that the velocity is whating? Increasing. Okay, so here's what we would say. When t equals 3 seconds or at t equals 3 seconds, whichever you prefer, comma. And again, we answer it straightforward with units on our independent variable. Okay, the velocity, you don't have to say of the particle or the particle's velocity. Just say the velocity is increasing now. Increasing by, and then here's the deal. We need to answer it in units of velocity every second, okay, or per second. So by 2, very good, by 2 feet per second, those are velocity units. And then you could say per second if you want. But remember, I said kind of if you're unsure, and this is kind of what Mrs. Skurhawk is kind of getting frustrated with right now. Not frustrated, but it's one of those details, you know, the words, how College Board wants you to answer the questions. And I can't blame College Board for doing it. It makes sense to me, right? So at t equals 3 seconds, the velocity of the particle along the horizontal number line is increasing by 2 feet per second each and every second, right? Perfect. Well done. What if it asked you for this? Let me just throw this in here. What if it asked you for the average acceleration on the interval from 0 to 3? Right? Acceleration by itself is the rate of change of velocity. But how would we find average acceleration? We know how to find instantaneous acceleration, right? VOTC. Find the derivative, plug it in, you're done. But average acceleration from 0 to 3. Okay, here's what it's going to be. Average is, it's still the rate of change of velocity, right? Acceleration is still the rate of change of velocity. Anytime you have to find an average rate of change, it's your difference quotient, okay? Let me write that first. Anytime you're finding an average rate of change, anytime, it's going to be the difference quotient. And for us, that's DQ, right? Every time. So if you're trying to find average velocity and you have the position function, it's the change of velocity over the change in time. So for us here, the average acceleration is going to be the change in velocity over the change in time. Here's what it would be. It would be your final velocity, which is your velocity at 3, minus your initial velocity, which is 0, all over the change in the time. Difference quotient, right? A quotient of two things being subtracted. And again, if you're not sure if it's going to give you the right answer, look at the units, right? The units of the numerator are velocity units, feet per second, and the units of the denominator are time units, seconds. Is that right? Feet per second per second? Sure is. All right, let's see what we get. V of 3, all right? Good thing I have my velocity equation now, right? V of 3 is what? 3 times 2 is 6. 6 minus 4 is 2. So that's 2 minus V of 0. We plug in a 0 into the velocity and we get -4. So minus -4. And then all over 3. And that you could stop there on a free response if you put units. So what do we get? 4 plus 2 is 6. 6 divided by 3. 2 feet per second squared. Yeah. 2 feet per second squared. Is that reasonable in hindsight? It's very reasonable, right? Because what did we discover by BOTCing over here about the acceleration? It's a constant, right? So if it's a constant, you're on cruise control, you're driving 60 miles an hour for 10 days, right? That's a long time. Your average is going to be the same as your instantaneous, right? All along the way. So yeah, but we verified that, right? It's not always going to be that way. But that's the difference between average rate of change and instantaneous rate of change. Instantaneous is always BOTC, calculus, and average is difference quotient, okay? All right, questions on that? We get a quick update on the t-shirts, like right at maybe before the bell rings for lunch, whenever that is, okay? Yeah. All right, at t equals 3 seconds, is the speed of the particle increasing or decreasing? Now, speed, right? Is that the same as velocity? No. Speed is a component of velocity. Velocity is a vector. Acceleration is a vector. Position is a vector. Speed is a scalar quantity, we call it. It does not have a direction. It only has a magnitude. Speed can be in any direction, okay? So here's what we know. We know from part D that at any given time, the acceleration is positive, which means at any given time, the velocity is increasing. But is it possible to have a velocity increasing while speed is decreasing? Yeah, it is, right? It can be. So think about speed as like well, let's just look at it. Let's say you have an object in your hand and you throw it into the air. Okay, you throw it into the air. As you throw it up, you know, the positive direction is up. What's happening to the speed? It's slowing down, right, until it gets to the top, and then it reaches 0, the top, and then as it falls back down towards your hand or earth, whatever, the speed is increasing, right? But let's think about velocities, right? As you throw it up, is the velocity positive or negative? The velocity is positive, okay, because it's going in the upward direction. Is the velocity increasing or decreasing at that moment? The velocity is increasing. Velocity is decreasing, right? Okay. And then velocity is also 0. As it falls back down to Earth, is yes. At a higher rate. Yes. Sounds negative. Yes. You want to say that out loud?
Yeah, sure.
Yeah, I'm sorry.
Okay,
Yeah.
okay. Sorry. The velocity on the way down, the velocity it decreased at a faster rate because we're only measuring how fast it's going up. But the speed, which can be in any direction, begins to increase as it falls back down. So since the velocity is only in one direction, it has to.
Yeah, that was a good band too. I'm sorry they broke up, but you're exactly right. One Direction. So as the object falls back down to Earth, right? As the object falls back down to Earth, we know the speed is increasing, right? Gravity. But what sign is the velocity when it's falling down to Earth? It's negative, right? And so the velocity is becoming increasingly negative. If a velocity becomes increasingly negative, that means it's decreasing, right? It's decreasing. Negative 20 feet per second, negative 30 feet per second, negative 100 feet per second. That's decreasing, but the speed is increasing. So yes, it is possible for velocity to be decreasing and speed increasing, all different combinations. So when you are asked about speed, which is just the magnitude of velocity, and you want to know if it's increasing or decreasing, there's a couple of ways you could do it, right? Because you're going to have to justify. You can't just use common sense, right? Like, duh, right? That would be your justification, duh, right? All you have to do is compare, okay? All you got to do is compare V of t and A of t at the moment in question, okay? Compare V of t and A of t. Think of velocity as you running and think of acceleration as wind, okay? Like you're running with or against the wind. When, let's say I'm running to my left here. If I'm running to my left, my velocity is negative. If I'm running with a tailwind behind my back, that's also going to be negative acceleration. What's happening to my speed if I'm running with a tailwind? It should be increasing, right? It's propelling me forward, okay? So when the acceleration and the velocity are both negative, speed should be increasing. Now, what if I'm running to the right and my velocity is positive and I still have a tailwind, positive acceleration? I should still have speed increasing, right? So now when the velocity and acceleration are both positive, speed is increasing. That's an easy thing to remember because what makes the dream work? Teamwork. Teamwork makes the dream work. So when the velocity and the acceleration are the same sign, both positive or both negative, they're working together, speed is increasing, okay? But what happens if I'm running into a headwind in either direction? It's going to slow me down a little bit. My speed will be decreasing, okay? So when the sign of velocity and the sign of acceleration at that moment are opposite signs, speed is going to be decreasing, okay? So that should be easy to remember. Working together, speed increases. So at t equals 3, we need to compare. So let's set up our analysis. I need to know what v of 3 is, and I need to know what a of 3 is. I'm going to write them below each other. These are instantaneous velocity, okay? Now, did I already compute these? I think so. If I come back up here, v of 3 was 2, and a of 3 was, I think I just calculated that to be also 2. They were both 2, right? How about that? Now, here's the important part about your analysis. It's not the magnitude that we're interested in, it's the SIGN sign, right? So here's all you have to do. Greater than 0, greater than 0. They're both greater than 0. They're both positive. They're working together. What's happening to the speed then? Increasing. So that's your, once you add the inequalities, that turns it into your justification. Okay. And notice I didn't say v of t at t equals 3. I just put v of 3, right? So once you put the inequalities, all you have to do is say, so speed is increasing. College Board does not make you say in general that the signs are the same. College Board wants you to tell them what the signs are, okay? What the signs are. And that's one of the benefits I get from being a reader, because before I was started grading those papers in the summer, I used to just tell my students, hey, just say, at t equals 3, the velocity and acceleration are the same sign, therefore speed is increasing. Because I thought that that would communicate to the reader a better understanding that it didn't matter if they were both positive or they were both negative. Doesn't matter. It's just that they're the same sign. And then I started reading calculus papers and I was like, oh crap, I owe all those kids, my students, some points back, because College Board wasn't counting that correct. College Board wants to see what the signs are. Okay. And you don't even have to say at this point, these are both positive. You just say V of 3 is greater than 0, A of 3 is greater than 0, therefore speed is increasing. So anyway, one of the benefits of grading calculus papers for 9 hours a day for 9 days straight. Yeah, you get to learn stuff like that. Yeah, and the food was good too, right? They didn't have little doodle things that stuck to your nose. Oh, candy corns. Yeah. No, that was impressive. He got a green candy corn wedged between his nose and his upper lip. And I thought we were going to have to call fire and rescue, but he worked it out. Okay. All right. Now I'm going to show you another way to justify speed increasing or decreasing when you have the graph. Okay. When you have the graph of velocity. But right now we don't. So that's how we're going to do it. Okay. Questions on that? There's a summary up here if you want to read it, right? But it's all about the sign. Okay. Letter F. During what times is the particle moving to the right? During what times is it moving to the left? And when does it change direction? Okay. So in order to answer this question, we need to do what? Ask the particle? Or what do we need to look at to make this assertion, this judgment? The sign of what? When is it moving to the right? When is it moving to the left? Well, if it's moving to the right, I should say, if it's moving to the right, its position is increasing, yes? And if it's moving to the left, its position is what? Position is decreasing. So if I knew what the sign of the rate of change of position was, I'd have it. What do we call the rate of change of position? Velocity. Yeah. So there it is. It's moving to the right when the velocity function is positive, and it's moving to the left when the velocity function is negative. And when is it not moving at all? When the velocity is 0. So when does it change direction? When the velocity does what? Switches from positive to negative or negative to positive. Yeah. And you see, again, back before I graded papers, I just told my students to say that the velocity function changed signs. College Board wants to know how. If you always get in the habit of talking about what a sign is or how a sign changes all year long, what a sign is or how a sign changes, in what manner, positive, negative, negative, positive, you'll be golden, right? Golden, right? As I open my eyes, open. So let's write that. Particle changes position. This is just us thinking out loud. Particle changes direction, I should say. Changes direction when V of t changes from, I'm going to say plus to minus or minus to plus. Try to never, ever, ever justify something by saying the words increasing and decreasing. You could do that in your sentence, right? Position is increasing, velocity is decreasing. But in terms of a justification, try not to do that. Always try to talk about a sign or sign change. Okay, so now we know what we need to do. We need the velocity function, don't we? We have it, right? The instantaneous velocity function, there it is. It's 2t minus 4. So let me bring that back down here. I'll write it. V of t is 2t minus 4. Now, of course, if this were an actual free response question, you wouldn't need to write down all that stuff over there. That's just us thinking out loud the first time we do it. What do we know about this function? It's linear. Yeah, it's linear. So I know the slope is positive too, right? In fact, I could quickly sketch it. Not that I need to, but if this is V and this is T, here's -4, right? -4, and then it has a slope of 2, like this. Yeah, very good. We could set it equal to 0, and we solve and we get T equals 2 seconds. Now, because we know what the graph looks like, we know then where the velocity is negative and where it's positive. Yeah. Here's the x-intercept at 2. It's negative to the left and positive to the right. If we didn't know that, we would have to set up a chart and test intervals. And I can show you that here in just a little bit. Let's go ahead and answer the question, okay? Particle moves, let's do right first, moves right for t greater than 2 seconds. And if it asks you to justify, it didn't ask you to justify here, but let's go ahead and throw that in there. The justification would be since v of t is greater than 0 on this interval. Now notice I used a pronoun there, on this interval. That's a very judicious use of a pronoun. Is the antecedent clearly defined there? What interval am I talking about in the same sentence? T is greater than 2. In general, you want to be very careful with pronouns. Okay, moves right on that interval, and then we'll just say, and left. Where is it moving left? For t less than 2? That's where this graph is negative, right? For t less than 2. For t less than 2 seconds, comma, since v of t is less than 0 on this interval. All right, now on that one that I just answered, you would not get it correct. Why? Is there any doubt that this graph, come on, it's delaying now. Is there any doubt that the graph is below the t-axis to the left of the t-intercept at 2? No. But do you remember yesterday at the very beginning, I said, as you're reading the original problem, there's like something that you might just gloss over, right? And it may come back to bite you. This problem only takes place at t equals 0 and to the right. So guess what we need to make sure we do? I need to make sure that I only look at the graph of this function from 0 and to the right. In other words, I'm not going to look at that piece I didn't highlight. So when I come back in here, I don't want to just say left for t less than 2. I want to say for t less than 2 and then say greater than or equal to 0. That's going to be a half open interval. Okay. Why would I include 0? Because is the velocity negative at 0? It is a negative number. Yeah. But I'm not including 2 because at the x-intercept or t-intercept, it's 0. It's not negative. Okay. So that's that little bitty detail that you read in the beginning. It's going to be for a reason. All right. And then for what it's worth, just to finish this problem, particle changes direction, and then we'll go to lunch. Particle changes directions at t equals 2 seconds, comma, since. Do we have to say because v of t equals 0 there? No. Some people only put because v of t equals 0 there. It actually has nothing to do with the velocity equaling 0 there. I can be walking to the right and stop, and then continue walking to the right. It's the sign change, okay? Since v of t changes, we're almost there, changes from negative to positive. And now you could say at this point, or you could just say at t equals 2 seconds again. You'll see that I tend to really not even use pronouns. Sometimes it's just faster to write the point again. So if you get in the habit also of stating it twice, here's where it changes directions, bless you, at Fiegel's too, because that happens to be the exact same place where this happens, okay? All right, so that takes care of that one right there. All right, y'all have a good lunch. When you get back, we'll do total distance traveled. I'm resuming. All right. Okay, so the last one here, find the total distance the particle travels in the first 3 seconds. This is a type of question at this point in the year that doesn't usually show up, but later on it will. So total distance traveled, that is different than displacement, yes? Displacement is net change in position. That's what we did on part A. Distance traveled is kind of like speed. The direction doesn't matter. We just want to get an accumulation of everything. We know this particle is going left and then right, correct? I need to figure out from 0 to 2 how far it travels going left. And then I need to figure out from 2 to, what does it say, 3, how far it's going to the right. So how can we do that? Well, any ideas? I know it changes direction at 2. How about, could I find the displacement from 0 to 2 and then take the absolute value of it? And then take the displacement from 2 to 3 and take the absolute value of it and add those together? Yeah, that'll work. As long as we know when it's going left and when it's going right. So here's what that would look like. You could say total distance or just distance, right? It's going to equal the absolute value of the displacement from 0 to 2. So that's, remember, x of 2 minus x of 0. Final minus initial. And the reason we take the absolute value of it is, you know, if it's negative, we want to make it positive. And because we know that it's going left from 0 to 2, that's why we went from 0 to 2. And then we'll add it to the displacement from 2 to 3. So that's x of 3 minus x of 2. Okay. So that's how we do it. Now it comes down to a computation. And let me come all the way back up here and just copy this equation so I can compute down here, paste. Okay, there we go. So now we compute x of 2. Help me out here. That's 4 minus 8. That's negative 8 plus 3 is negative 5. And then x of 0 is 3. All right. 2 squared is 4. 4 minus 8 negative. Oh, that's not right. What is x of 2? Did y'all get the same thing? 2 squared is 4 minus 8. That's negative 4 plus 3 is negative 1. I put negative 5. Okay. And then minus x of 0. Y'all are so trusting. 3. Okay, that looks good. And then plus haste makes waste, right? Now you plug in a 3. I think we, let's see, 9 minus 12. That's 0, right? Minus x of 2 becomes minus negative 1, right? And if this were a free response, you could stop right there as long as you put feet on it, right? But we'll keep going. Let's see. That's negative 4. Absolute value of that is 4. And then this becomes 1. So yeah, it moves 4 units to the left from 0 to 2. And then it moves 1 unit to the right from 2 to 3. Right? And that's why the displacement up there was negative 3. But here we're adding them together and we get 5 feet. Sweet. There you go. So the total distance traveled is the absolute value of the displacements added together in between every turning point. Okay. Kind of cool to think about it. All right. So it says, are you exhausted as the particle? Yeah. I mean, that was a lot, right? It took us 2 whole days to do that. Now that is a, yeah, that's way too much for one free response question on an exam, but any combination of these questions or any single one for multiple choice is fair game, right? So we need to know how to do all of it, right, Ethan? Right. All right, questions on that? No quiz tomorrow. Probably not going to quiz Friday because it'll be my first day back, but maybe next Monday. Okay. Maybe. I mean, there's still. I mean, that would. Oh heck yeah! Let's move on. Particle motion is very important. Maybe I'll tell you. All right, example 7. Let's take a look at this. The graph above shows the position of the particle. So like the previous problem, we have position, but unlike the previous problem, now we have a graph instead of an equation, right? And it's y of t moving on a vertical line. Well, that's different too. So instead of going left, right, it's going up, down, and we have units of inches against time and seconds. So instead of feet per second, we have inches per second. And notice we are also staying, in this case, not just greater than or equal to 0, but we're staying on this little interval from 0 to 7, which is where the graph is, okay? So whenever you have a graph or an equation or a table of values, you always need to make sense, deliberately, what does that table, what does the graph, what does the equation give you, okay? So if you look at the graph here, you're like, okay, the y values are the positions, right? You don't even have to write that down because it's obvious, but maybe it helps. The y values are the positions. Now, what's nice about it moving on a vertical line is you can almost like track its vertical position, on this vertical graph, right? Like the itsy bitsy spider goes down from 2 to 4, whatever, Now, here's the other thing. If you have a graph, especially, the y values are the positions. What do the slopes represent? Velocities. Yeah, the slopes are your velocities. Again, you don't have to write that down, but you want to at least think about that, okay? The slopes now are your velocities, and they're made up of line segments, so we can actually calculate them, right? Now, unfortunately, this function is not differentiable on the entire interval, is it? It's not differentiable at the endpoints. No function is, although it is continuous at the endpoints. But on the interior, what are the values where this function is not differentiable? 2, 4, and 6. Yeah, because they're sharp turns. The slopes don't line up. So this particle is changing at some unfathomable rate. That's not physically possible, but that's between the particle and Mother Nature. All right. All right. So now let's go ahead and answer the question. On what open intervals from 0 to 7, open intervals, is the particle moving down? Justify. Well, a particle is moving down when its position is decreasing. That's when the velocity is what? Negative, right? Well, if the slopes of the velocity, where are the slopes negative? From 2 to 4 and 6 to 7. So that's what I was saying. It's kind of nice that it's moving on a vertical line because the particle is moving down when the physical graph is decreasing, right? So again, you could justify and then answer, or answer then justify. Let's go ahead and answer. Now, because this is the only question that's being asked on this part, you don't have to write that all over again. The particle is moving down on. You could just go ahead and answer it. And you can answer it as an interval, or you can answer it as an inequality. I'm going to go ahead and say T epsilon open interval from 2 to 4, and then union 6 to 7. Because there was more than one interval there, I didn't want to use the inequality notation. It's a little more cumbersome. And it did say open intervals, right? And then what should I put on the end of there? Are there units? Well, it's time, right? X intervals in this case are T intervals, which is seconds, right? And then you could say because or since. And what would be the reasoning? Very good. Something to that effect. You don't want to just say since V of t is negative on this interval, because where the heck is V of t? Have we defined V of t? Did they give us V of t? What is V of t? Okay. You always want to relate it to what's given. So in the previous one, we had the equation. Here we have the graph. So I like what you said. Since the slopes are negative, you could say that too. Now watch. If I just said since the slopes are negative, you're not going to get credit, because as AP readers, they're trained to say the slopes of what? The slopes at heavenly at in Heavenly Resort in Lake Tahoe? What are you talking about? The slopes of what? The slopes of what? What graph? Yeah, just say the slopes of y of t. Even if you said the graph, they're going to be like, what graph? The graph I gave you, the obvious choice right here, or some graph that, is in France right now? What graph? Right? You got to be very, very specific. Don't be vague. It's actually faster just to say slopes of y of t, okay, are negative on this interval or these intervals, whatever. Okay. Always refer back to the point or the interval. And remember, I said you always want to talk about a sign or a sign change. If you would have said since y of t is decreasing on this interval, I wouldn't recommend that, especially later when we get into what's called the first derivative test. So get in the habit talking about a sign or a sign change. That would work. T epsilon that, since the slopes of y of t are negative on this interval. Perfect. All right. On what open intervals is the particle at rest? At rest. What are we going to be looking for? No motion, which means the slope is 0, right? Because the slopes are velocity. Something, bless you, is at rest when it's not moving. Bless you. And that's going to be where the velocity or the slopes are 0. That's from 0 to what? 0 to 2. Okay. So we'll say a t epsilon 0 to 2 seconds. And again, it said open intervals. And then you could say since the slopes of y of t, you could say since the slopes of the graph of y of t, but that's just more writing. Okay. Since the slopes of y of t are 0 or equal 0, you could say equal 0 on this interval. Now, it is a little bit of writing, right? I'll admit that, to say the slopes of y of t every single time, right? The slopes of y of t, the slopes of y of t. If you want, not for your own benefit, but for the benefit of the reader, if you want one time at the tops, you could just say the slopes of y of t equal v of t. If you say that one time at the top, it's kind of like having like a map legend, right? Like, what is that dotted line? Oh, those are mountains, right? So you could do that one time. And now you're defining v of t. And now if you want to use v of t down below, instead of saying the slopes of y of t, then that's okay, right? Does that make sense? Just remember the goal is communication, right? At what times on the open interval does the particle change direction? Justify, right? Particle's going to change direction in general when the velocity changes signs. That's the slopes over here, right? So where do the slopes change signs? Does the slope change sign at 2? No, because it's going from 0. So the slopes change from negative to positive at 4 and positive to negative at 6. So again, before I graded papers, I would just clump those together and say, since the slopes of y of t change signs at these points. Guess what College Board wants? They want to know how it changes. So because it changes in 2 different manners, we got to split up the argument. Is it a bit of writing? Yeah. I'm going to go ahead and write it up here where I can see the graph, okay? Particle changes directions. It's the only question they're asking. So I'm just going to go straight to the answer. So T epsilon, or not T epsilon. These aren't intervals. We'll say at T equals 4 seconds, and then I'll justify since V of T. Can I use V of T? Yeah, let's pretend that I did do this, right? It would be helpful to do that. It's just like on the previous problem where we did this, right? We did x prime of t equals v of t. It's kind of the same idea, right? So now it saves some writing. So since v of t And now I could say is less than 0, right? At this point. You know what's faster than writing at this point? Is just to say at t equals 4 seconds again. It's not the best writing in English. That's why pronouns are invented, but in here it's good, right? And at t equals 6 seconds, okay, comma, since, wait, I need to do change in sign. At t equals 4 seconds, since v of t, my bad. We need to talk about how the sign changes. Since v of t changes from negative to positive, right? At t equals 4 seconds. Right? You got to talk about how the slopes change. Okay. And now we can say at t equals 6 seconds, where v of t changes from positive to negative. Now notice that pronoun. Do you see that? Where? That's kind of a slick way to get it in there. That references the point again, doesn't it? Again, you're always wanting to say two things. Here is where it happens, because that is also, not coincidentally, the place where this happens. Okay, the sign changes in this manner, and you can abbreviate positive and negative like that. Believe it or not, College Board accepts that. I would rather you write POS and NEG than use the plus and minus sign, because the plus sign looks like a T sometimes, and the minus sign looks like an inadvertent dot. Okay, so there you go. That's a little bit of writing. There's a little tedious stuff too, right? This is where Mrs. Skurhawk is kind of getting frustrated because of the all the words, the justification. All right, so then we'll bring that down there. All right. During the first 6 seconds, what's the particle's displacement? During the first 6 seconds, displacement. Hey, how do we find displacement? It's your net change in position, right? So let's label it DISP for displacement. It's your final position at 6 minus your initial position at 0. So that indicates your method. All right. Do your math homework. And now we come up here. What is y of 6? Y of 6 is 0, right? And what's y of 0? 6, right? So this ends up being a 0 minus 6, which ends up equaling negative 6 inches. All right. So that makes sense, right? We're looking at it over here, and it started here. So yeah, if it started at 0.6, 6 seconds later, it's on the x-axis. So its displacement was negative 6. Now that's not the total distance it traveled, did it? No, because it went down 6, and then it went down 6 more and came back up 6 more. So there's like an additional 12 units of movement in there. But that's not what it asked here. It said displacement. Explain what this means in terms of its change in position. Okay. So you could say then, during, using their words there, during the first 6 seconds, comma, the particle is displaced, and now it's a vector, 6 inches below its starting position. Or you could just say it's displaced. How about it's displaced 6 inches below its starting position would work, but how about 6 inches downward? Would that work? It's displaced 6 inches downward. I like that. I mean, it gets the job done. Or 6 inches down, if you don't say downward. 6 inches below its starting position. All of that works. Okay. That works too. That works too. Yeah. But downward, right? If you had a dog named Ward that jumped up on people when it came over, that's what you say. Downward, down, down. Ward was the name of the dad on Leave It to Beaver, believe it or not. Have you ever heard of that show, Leave It to Beaver? It was a classic show. His name was Ward Cleaver. Look it up, good times. Me TV or Google it. How are we doing on time? 4 minutes. During the first 6 seconds, through how many inches does the particle travel? That's total distance, isn't it? Does it say to justify? Thank goodness. Okay. So let's just say distance traveled is. Now, we can kind of do it up here. This is, it travels 6 inches there, and then there's another 6 inches there, and then it travels another 6 inches there. So here's one of the things that is important when you have a graph and you're not really doing calculations with an equation. If you indicate your method by using numbers that you've computed on the graph, and those numbers show up in your calculations down below, that's enough to get credit for your work, okay? Because just in general, they don't like what we call bald answers. In other words, just adding these together in your head and putting down the answer, not the best practice. It doesn't communicate how you're doing it. But if you write that as 6, 6, and 6, 6, 6, 6, which that's the number of the beast is an Iron Maiden song. And my wife sent me an article the other day. There's a female principal at some private school somewhere in America. The board, the school board, is trying to get her removed from her job as principal of this private school because on her Instagram page, she showed a picture of her wearing an Iron Maiden, the number of the beast shirt. And she's doing this, and they're saying that she's satanic and they need to get rid of her. But anyway, yeah, what those people don't know is the song Number of the Beast 666 is about a guy who he thinks he's dreaming and he sees devil worshipers and he's telling himself in the dream that it's not right, that it's wrong. So it's actually, against the number of the beast. But anyway, 6 plus 6 plus 6 inches, which I think comes out to 18, right? Good. What's that? Oh, it just said from 0 to 6. Yeah. So there was an additional 3 at the end, but and that's why reading the interval is super important. Now, we're not going to have time to finish this one, so we'll pick up with 7F on the video tomorrow, and hopefully on the video we can finish this section. Be working on the worksheet for this section. This is it's tedious. There's a lot of words and sentences and equations and graphs and charts, but it's like the most important application of one of the most applications of the derivative we'll use all year. Okay.